about the behavior of electrons in atoms, and specifically whether electrons in the same orbital could be entangled. Now, quantum mechanics is notorious for being a bit mind-bending, but I think by the end of this deep dive, you'll have a much clearer grasp of what's going on. So let's jump right in.
Yeah, this is definitely one of those topics that can really trip people up. The line between classical correlation and true quantum entanglement can get pretty blurry.
Okay, so maybe that's a good place to start. Could you walk us through what entanglement actually is and what makes it so different from just regular old correlation?
Entanglement, it's a bit more than just a connection. It's like these particles have their fates intertwined at a really fundamental level. Let's say you have two entangled particles, and then you measure a property of one of them, like its spin. At that very moment, you instantly know the corresponding property of the other particle, no matter how far apart they are.
Whoa, okay, faster than light. That's wild.
It really is. It's this instantaneous correlation that makes entanglement so mind boggling. And I remember some of the listener questions mentioned superposition too.
Oh, yeah, superposition. That's another one of those quantum mechanics concepts that can feel kind of impossible. Can you give us a refresher?
Think of it like flipping a coin. Classically, it lands on either heads or tails, right?
Right.
But with superposition, it's like the coin is both heads and tails at the same time until you actually look at it. Entanglement takes this a step further. Those particles are in this fuzzy, undefined state until we measure one of them. And then it's like that act of measuring forces the other one into a definite state, even if they're miles apart.
Okay, so I'm starting to see how entanglement is this weird non-local connection. But how does this apply to electrons whizzing around an atom?
Yeah, that's where things get interesting. We need to think about orbitals. You've probably seen those diagrams of the different orbital shapes, s-orbitals, p-orbitals, and so on.
Definitely. From chemistry class, they weren't always easy to visualize, though.
They're not meant to be actual paths that electrons follow. It's more like regions of space where you're most likely to find an electron, and each orbital can hold a maximum of 2 electrons.
Right, and one of the questions we got mentioned that if you know the spin of one electron in an orbital, you automatically know the spin of the other one. That sounds a lot like entanglement.
It does, doesn't it? And that's a really insightful observation. It gets to the heart of why people get confused. It's true that the spins of those 2 electrons are correlated, but it's not because of entanglement. It's because of something called the Pauli exclusion principle.
Ah, yes, the Pauli exclusion principle. I've definitely heard of that, but a quick refresher would be great.
Okay, so basically it's this rule that says no 2 electrons in an atom can be in the exact same quantum state. They can't have all the same quantum numbers, which describe their energy, their orbital, and their spin.
So like 2 runners in the same lane can't be in the same position at the same time.
That's a great analogy. Since electrons in the same orbital already have the same energy level and orbital shape, the only thing left that can be different is their spin.
So one spin up and one spin down, like a cosmic dance routine.